You're watching Invention Chronicles, exploring the greatest ideas ever imagined. Imagine a phone screen that mends its own scratches, or a bridge that heals the tiny cracks that form over years of strain. This is not science fiction. This is the world of self-healing materials. Inspired by nature's ability to repair itself, scientists are creating smart substances that can sense damage and automatically restore their integrity. This ability to self-repair promises to make our creations more durable and safer, reducing the constant cycle of replacement and waste. The benefits range from self-sealing pipelines to spacecraft that can repair damage millions of miles from home. The journey into this new material age is already underway. Researchers have developed ingenious methods. Some use tiny capsules filled with a healing agent, while others rely on clever chemistry, creating molecular bonds that can break and then reform. Each approach is tailored to the unique properties of the material, whether it's a flexible polymer, a protective coating, concrete, or metal. Polymers are the building blocks of our modern world, but they're prone to damage like scratches and cracks. This is where self-healing polymers come in. One common method uses a capsule-based system. Millions of microscopic spheres filled with a liquid healing agent are embedded in the plastic. A chemical catalyst is also scattered throughout the material. When a crack tears through the polymer, it ruptures these capsules. The healing agent flows out, comes into contact with the catalyst, and hardens. This effectively bonds the two sides of the crack back together, restoring the material's integrity. When these materials are damaged, their molecular bonds are broken. But with a trigger, like heat or light, the molecules become energized. This allows them to move, find their former partners, and reform the bonds, effectively sealing the damage. Imagine a phone case that heals its own scratches, or a water pipe that prevents leaks by repairing small tears. These materials promise a future with less waste, where the items we rely on can endure far more wear and tear. Coatings are thin, protective layers that shield surfaces from the environment, but when they get damaged, self-healing coatings can automatically repair themselves. Many use embedded microcapsules filled with a healing agent. When a scratch occurs, it ruptures the capsules. The agent is released, seeping into the gash. Exposed to air, it hardens, sealing the damage. This prevents corrosion, like rust on a car, and makes the scratch far less visible. Another strategy uses flowing coatings. Specialized polymers have a semi-liquid quality, allowing them to slowly level out and erase shallow scratches when warmed by the sun. This maintains glossy finishes on cars and electronics, and extends the lifespan of large structures like bridges and wind turbines. Self-healing coatings provide a permanent shield against rust, a major cause of structural failure. At home, they keep surfaces looking new. Concrete is the foundation of our cities, but it has a major weakness. It cracks. Water seeps into these cracks, and in cold climates it freezes and expands, widening them. Self-healing concrete solves this by embedding dormant bacteria into the mix. When water enters a crack, it awakens the bacteria, which produce limestone, naturally sealing the damage. In concrete, some methods use bacteria that produce limestone to fill cracks. Another uses a vascular network of tubes. When cracked, these tubes break, releasing a healing agent that hardens and seals the damage from within. Self-repairing concrete uses vascular channels or bacteria to heal cracks. This means bridges, tunnels, and dams need less maintenance, making our infrastructure safer and more resilient. Metals present a much greater challenge. Their tightly packed atomic structure makes it difficult to introduce healing agents. They're also subjected to higher stresses and temperatures. Despite these hurdles, scientists are making exciting progress, creating metals that can repair microscopic damage, known as fatigue. The goal is to stop tiny cracks before they grow. For metals, research is exploring shape memory alloys, which return to their original shape when heated, potentially closing cracks. Another approach embeds tiny channels with a solder-like material. When a crack forms, heat melts the solder, which flows to seal the damage. Both methods are promising but remain largely in the lab. While largely in the laboratory phase, the potential of self-healing metals is enormous. Imagine engine parts in aircraft or power plants that repair their own microscopic flaws. This could make them last longer and improve safety, paving the way for more durable, dependable machinery. Self-healing materials are moving from laboratory curiosity to practical reality. The benefits are clear: longer-lasting products, reduced waste, and enhanced safety. This shift represents a move away from a disposable culture toward one of durability, creating a more sustainable world. Of course, significant challenges remain. Cost is a major barrier, and many current systems are a one-time affair, losing their ability to repair the same spot twice. To overcome this, researchers are developing the next generation of materials. These may feature intricate vascular networks that pump healing agents multiple times, much like our own circulatory system. Others might use sensors to diagnose damage and trigger the most appropriate healing response. We are moving toward truly smart materials that actively preserve themselves. The age of self-healing is dawning, impacting industries from automotive to aerospace. Soon, we'll live in a world where scratches fade, cracks seal, and the things we depend on have a built-in capacity to endure. This is a fundamental change in our relationship with the material world. We are learning to build things not just to be strong, but resilient, built to last. The rise of self-healing materials. Thank you for watching. Stay curious and keep exploring the world of invention and discovery.